You're fine today? How do you feel?
Perfect.
Good? Nice? Did you have breakfast? Did you have some snacks? Did you have coffee?
Yes.
Okay, right. So if you want to eat something else, just grab a cup of coffee. It's gonna take about like an hour now. And first, warm welcome to you and to Conrad Wolfram here at the bootcamp. So maybe just short introduction what we're doing here today. I don't know how many of you know what Burda Bootcamp is doing, but I'm just going to tell you without asking if you know. So what we do is sort of an incubation, mini incubator for technologists and business people who want to start with their own idea. And we also support existing startups to help them get to the next level. But we run tech events, meetups, hackathons, coding events as well. So it's basically the whole spectrum of different things. I think all of you know who Conrad Wolfram actually is, but I just make a short introduction. So Conrad is one of the faces behind Wolfram Alfa, which is the computational knowledge engine. And each time I use Wolfram Alfa, I'm sort of fascinated by the range of possibilities it offers. Me as a non-mathematician as well, but I guess for you it's like much more interesting because you use it more professionally. And Conrad is also the CEO of Wolfram Research Europe, which has much more than just Wolfram Alfa, but you're going to tell us about that hopefully.
Sure.
And he's the face behind the website called Computer-Based Math, which is basically about redefining the math education and to bring it more to computer-based computation. So what about today? We'll start with a short keynote by Conrad, where he'll tell you all about deep computation for the enterprise and data science. And then we'll just have a short and informal Q&A Q&A round where I will ask some questions, and you please feel free to ask your questions as well. Right? Okay, so let's get started.
Sounds
Conrad,
good.
the floor
Great.
is yours.
Thanks
Please.
very much. Thank you. So that was a great introduction of the various parts of me and what we do. So I wanted to talk about, actually I really wanted to talk about, to start with, zoom right out and talk about computation. So computation is this thing we've all grown up with that we just assume is there. You can work stuff out logically, you can compute new things. But it's pretty recent in actually being kind of useful. I think if you'd asked most people a couple of hundred years ago, what can you compute? Some scientists might maybe think that you could work stuff out with math and so forth, and they'd started to, but it was a pretty small fraction of the world that thought you could work stuff out that way. So computation is a new idea in the world's evolution. And I think it's worth asking, what's worked well so far and what do we still have to fix? And how much more road is there for computation? How much further can it push the world? So it's kind of like, computation worked well for a long time for things like physics, bits of physics, accountancy, things where you could have very definite numbers and compute stuff with small amounts of data. It's worked well recently for scaling up things where you can do that same very definite calculations but with huge amounts of that because of mechanized computation. Structured tools, things that are already figured out where you can see a very definite structure. And also sort of simple to specify data questions. But one of the things that's happened in society, and I was just actually talking about this in the earlier session, is people have taken numbers and used numbers beyond their ability to judge in many aspects of society at the moment. So we were particularly talking this morning about assessment in education. You know, you've got a number at the end, you got an A grade, or you got that's pretty much a number. You know, that's supposed to summarize how you did, what you are, how useful you are to the employer, or whatever. So we have a long way to go, I think, in terms of but it's worked well, computation's worked well in working with those very simple to specify things. So what's still to go? Well, fuzzy questioning. We've tried to do some of that in Wolfram Alfa, and we can come back to that. Asking a question that's not quite clear, and trying to somehow get computation to do stuff with that. You know, rapid deployment of new ideas, still quite a lot of effort to set up computations, to abstract them, to get a computer to work on them. It doesn't flow very cleanly yet. And also trying to communicate what one has done computation to other people. Most companies, you know, you go to the boss of the company, maybe this is an exception, this company, but you go to the boss of the company and you present them with your calculation for what's going to happen. That doesn't work too well. We're not too good at communicating computational ideas often. Another thing which is a bit more technical is, it's funny, the world is structured like a sort of grid, like Excel. Everything is thought of often as matrices of two-dimensional things, and there's a lot of richness you can get from much better data structures. So I think those are some of the areas that can move forward. So my big pitch here is that computation has a long way to run. There's an English expression which is, you ain't seen nothing yet. So I think we're only at a fairly early stage of mechanized computation, and I think as you look in the future years, it will come a long way. So what I want to do is focus on perhaps the most important area of computation right now in terms of energy that's happening, which is data science. And of course, in recent years, the ability to be able to compute all sorts of things with data has eclipsed many other areas of computation. And I just kind of wanted to walk through some of the issues involved there. So one of the questions I often ask is, has more data led to better decisions in the world? Right, it's clear that we have fantastic amounts more data than we had a little while ago. Some of us, like me, even remember before the web, when we had kind of a data deficit. But the problem we've got now, I think, is kind of an information overload. It's kind of like you were in a forest and you couldn't see the trees from the forest. And the question is, how do we fix that problem? So I think most people believe they have access to much more data than they can get decisions out of. And that the decisions are not necessarily that good based on the data. And of course the problem is going to get much worse, right? Because we're all collecting lots of data ourselves. The amount of data that's coming into the system is much, much greater. So one of the ways I think we can help to fix this is by empowering everyone with the highest level computation. So that means we've got to have humans interact with computers at a high level of computation. Not only the experts, but every human at the level that they can interact with. And those are all going to be different sorts of levels. And one of the things I always implore people to do is think about the interface first. You know, it's all very well saying governments love doing this. The UK government did this some years ago. They said, you know, oh, it's great, we've got this open data initiative. We're going to throw all this data out, right? And, you know, it'll be great. It'll empower all of our citizens. Because that was after the history of the UK, which tends to be rather secretive over data. So it's sort of, you know, it's one of these UK turnarounds. The problem was, of course, there's a big difference between accessibility and availability. Right, just because something's thrown out and is available, it doesn't mean it's actually usable and accessible by the people. And I remember once going into the Guardian newspaper and they just released some treasury data about, I don't know, MP's expenses or something, whatever it was. And there were 20 expert Guardian data analysts sitting around with their computers trying to figure out what this meant. And I was thinking, this isn't accessible to most citizens yet. So we've got to think a lot about interface. And a typical interface type that you know, is a linguistic one. So this is an interesting interface, and this is, let me just put the mic down for a second, thank you. Let me just go to Wolfram Alfa for a second, and you know, a typical sort of linguistic thing is, you know, let's do a simple thing like population of Munich versus Oxford. So that's sort of a drive-by question that I'm asking of this, hopefully, there we go. And it has indeed decided that we're in Munich, Bavaria, and has compared the population. And it's thought, well, there are some interesting other things to talk about here. Maybe there's the history of the populations. Maybe there are some other things I can do. So this was all generated live. There's also disambiguation. Did I mean Oxford, the United Kingdom, or did I mean Oxford, Ohio, US, for example? There are many Oxfords. So this is a different Oxford it's now comparing with. And so there's a lot that sort of goes on in trying to understand the question, interpret it, and figure out what the answer might be. And so this is one style of interface, kind of a linguistic way of querying data. And it's very different to search, by the way. What we're doing here is we're trying to understand the question. We are then have computable data behind the scenes. We are then computing with that data to try and answer the question. We're then building live a document, and the document is then turned into HTML5 in this case and pumped out through the website. So it's actually a very different sequence to search. And you can do, you know, some fairly cool things with this as well. That was a rather simple example. So linguistic access is one important thing. Here's another thing I think is important. What I call knowledge apps. So in a sense, we've got used to apps being interactive things, but not necessarily apps that are sort of interactive so that you can understand knowledge. That's less common. So this is an example of a project we did on heart disease in, I think, a Middle Eastern country. And the point is, this is actually live computing off the data set, actual things, sitting in my document, which is my talk here. And we call this a computable document. And something where you have a narrative, like I'm leading you through a narrative. We're in a talk format at the moment, but I could be in a sort of scrolling document format. And in the middle of that, we have an actual app that you can really use. And this is an interesting way of improving decision making. Let the reader drive. You know, the traditional thing you have with a narrative document at the moment is you kind of put, I imagine it like a landscape, and you've kind of got a railway line, and the moment you're telling somebody they can read forwards and backwards in the train. They can either go one way in the train or they can all go back the other way. Maybe there's a branch they can take somewhere. What I'm saying is rent a four-wheel drive and drive, you know, there may be some roads that you're suggested down, but go off the road. You can try different things. You can compute live. That gives the much better sort of bandwidth of communication between the author and the reader, in a sense. Here's another thing. I'm just going to type something in here. This is, I just want to point out how accessible. Let's see if we can get this working. So I'm going to look up, I'm going to try and do...
Oh, it's me.
Part of you. So I'm going to try and look up if this is, oh, okay, there's nothing of that sort. So let me reduce the length of this. Okay, great. So what I did there was I searched the human genome for that sequence, and it came up with all the chromosome sites where the human genome displays that sequence. Isn't it amazing that one can do that on a laptop computer, standing here, straight out of one command, looking things up, integrated into a language? So that's kind of, having computable data built in is a really important part. Just having it ready, having it to use is a really important part of and being able to then, you know, this is all in a computable form, so I can select pieces out and do what I want with it. So another thing we've been trying to do is make it easier to supply such data, and it's sort of important to be able to drop data in a computable way. So one of the big problems in the whole data science thing is having the data actually ready for computation. And we've done a lot of work on that, and we're trying to help other people to get it in that way and supply ways to do that and supply a structure that can allow that to happen. Now, I mentioned before that one of the problems at the moment is all data pretty much is sort of rectangular in its structure. Not all data, but a lot of people think of data in a rectangular kind of thing, and that's very limiting. One of the things I will show actually, one of the things we've been doing for years is we've tried to unify every aspect of our ecosystem into these sort of symbolic expressions. And in fact, if I unformat, oh, it's awfully small, but if I unformat the cell I was just in, it's actually shown, you can probably just see some commands at the top there. But what this is a symbolic representation of the interface that I'm showing here. And I could do that for any aspect of what I'm doing. It's a very kind of tree-like or graph network style layout of symbolic expressions. And by having that sort of in that form, you can structure data in a very native way, much more natively than has traditionally been the case. And you need to do that. Again, having the stuff ready to use is sort of crucial in allowing computation to work. So here is a, let me see if I can demo this. So I wanted to show you what happens when you have an ecosystem where you put all these pieces together and do this computation for everyone. Let me see it. I'm going to see if this actually works. So what I was going to do, let's see if this is coming here. Okay, let's see if that actually happened. Yes, okay, fine. So here am I, and you'll notice that with a very short piece of code here, we have built a thing called image identify that is identifying various objects based on looking at my camera. Now, the interesting thing about this is, there we go, capacitor microphone, that's exciting. You could try something else here. The thing I wanted to show here is, yes, I mean, it doesn't always, so as you guessed, this has been figured out with machine learning. The thing that's exciting here is it took us about maybe 3 weeks to build this. That's all. So there are things that compete with this and do perhaps better in some cases than this. They didn't get built in 3 weeks. They mostly got built by startups in 2 years. So the reason that's possible is because we've got the semantic knowledge. We've got salt shaker, yeah. We've got the computation to do the image recognition built in. We've got the language that allows us easily to specify. We've got all these things sort of put together in a way that allows this to work. Now, what I was also going to do, and this has a high degree of likelihood of failure, but let's try it anyway. And I need to get myself. So what I was going to do is try and make this image and see if I could tweet an image of me with a microphone that still says person, capacitor microphone. Let's see if I can tweet this and see if on my Twitter stream it actually appears as I tried to tweet that, which may or may not have worked. And see if that appears on my Twitter stream as I think it may not have worked actually. There we go. And see if we can have tweeted that image. Maybe worked, maybe didn't. It's a little bit high wire, that one. I'll have to try it again if not. But the point is that that's all integrated, that I can tweet a computation that I've just done as an image and make that work through. Didn't work?
Yeah, are you online?
Yeah.
Not yet.
Then I'd probably have to come back to that. So, I guess one of the things I would like to see is us empower the future consumer to generate their own knowledge. So I think the future is going to be about not here's a piece of data, here's a piece of knowledge, here's the thing you needed to work out what we told you to work out. But here's the tool set that is applicable with the interface you need for your level to be able to work this through. And that's sort of where I think we need to go in the future. And hopefully, you know, by having the right tools, you can really make this a reality. One thing I just wanted to come to is how I talked about data and decisions. And has more data led to better decisions? One of the things I've sort of noticed is that there have been various eras of sort of management. You know, years ago it was kind of like, well, you just sort of guessed. What's my instinct about the situation? Should we back this, or should we back that? Or should we do this or that? And then we kind of been this age of what I would call simple targets. You know, it's kind of like, the number was 3, so that means we should do this one. Or it's kind of like, you know, the hospital has 3 metrics, and that proves that it's a good hospital, or whatever it is. So the question is now whether we are in a place where we can do more agile targets, where we can, in a sense, have a complete data set for different complex situations. Instead of fixing the metric, instead of the person sort of who's making the data, putting the data out, fixing the metric themselves, the idea would be that you give the whole data set and the tools to be able to query that in any way you like, and then kind of the user of the data is querying that data set. And that's very powerful, I think, in allowing sort of agile targets. You know, we were talking, as I said, about assessment earlier. Why do we do this thing where we put students in an exam room for 2 hours and we lock out, we chuck away all the data we collected on them for the last 10 years and we measure them just on that 2 hours and decide that that's what tells us what's going to happen? We've got a huge gob of data. Different industries or universities want to have different ways to look at the data of that student. They don't all want the same thing out of the student. Why are we not empowering them to do that? That's what the sort of thing I mean by agile metrics. One of the things also as a trend that I've seen is this idea that sort of expertise has got personalized over time. So it was kind of like word processing. You know, you didn't get your assistant to type the thing. If you were an executive, you went and did it yourself. You typed your own email and things like that. And kind of the web was allowing several things. It was allowing kind of, you know, personal fact-finding and personal distribution. Digital photography allows you to kind of personally do photos. And I think we're now in an era of knowledge where we've kind of got personal knowledge generation with the help of computation. And I think that's a sort of, you know, personalizing data science expertise is sort of an important part of what we're doing. So what are the barriers to this ubiquitous data science I'm talking about? I think there are really sort of three groups. There's the ecosystem, technical ecosystem. There's the data itself. And I think there is humans understanding what they're supposed to be doing with maths, coding, computational thinking. The problem is that the more the technology comes on, the higher the level a human needs to be to make progress with that. And I'll come back to that for a second in a moment. But so I want to come back to the bigger picture of computation. So what are the lessons about computation from data science? I think the lessons are there's a long way to go. Unification gets you tremendous power. Now, my image identify example is a unification example. If you can unify all the different bits, I think that you can get much more power than if you have these different pieces and sort of areas of data science in an organization. And ubiquity of access drives empowerment. I mean, this is kind of democratization, right? Of the modern world of democratization is the more people you give access to on a good piece of technology, the better the further you can get with that. I hesitate to say the better the result can be good, it could be bad, there are bad and good aspects. But ubiquity of access drives empowerment. And I think that is starting to happen for computation, and particularly with data science. So what are we doing at Wolfram? Just a quick rundown. We are trying to build this ecosystem for computation, so that any aspect of computation with any interface on any device, whether server-based, desktop-based, locally, in the cloud, not in the cloud, we are trying to be able to be that complete hub of computational expertise. And one of the exciting things, I mentioned this a little bit earlier, is the idea, so what are the technologies that allow us to do that? Well, one of them is these symbolic expressions I mentioned. So the fact that everything, if I look at, these are all different objects in our Wolfram language, but if you roll over this, I'm going to show you that this is the underlying code. And you'll see that whether it's a, you know, I don't know, a hierarchical table, or whether it's a, you know, a graph, or whether it's images, these are all actually just symbolic expressions. They're the same kind of object. And that's really, really powerful, because what it means is you can operate on one object you can operate in using the language on any kind of object automatically, and etc., etc. So it's kind of nice that all these things are just fully optimized. Maths type setting, that was a challenge, but that's also symbolically represented in this way. And of course programs, and of course interface structures. This interface itself is represented just in that way. So that's sort of this unification layer I'm talking about. Another key thing we're trying to do now, and we're fairly far along this road, is hybridizing cloud. When people talk about cloud technology, they often talk about, you know, sometimes they mean storage. We mean computing, as well as storage, as well as interface layers. And so in fact, in our view of life, there are many, many different parts that can be operating locally or in the cloud, or you can have some hybridization of all of those things. And it's actually quite challenging to work out which bits you want where. I mean, to give you an example, those sliders I was pulling, you've got to have good latency, low latency in your network to get really good performance on those things. Doesn't mean you can't, but on the other hand, you don't want to have a local program having to run beyond what your browser would do in order to give access to that sort of computable document. So there's a trade-off. And I think the thing that everybody's been going kind of crazy about the cloud, and that's great, I think it'll be like what's happened with interfaces, where these things build on top of each other. So I'm very much for the hybridized cloud, i.e. you want some things running locally, you want some things in the cloud, you want some things in public clouds, you want some things in private clouds, and you want to be able to mesh those up in an effective way. One thing we've just launched is the enterprise private cloud. So the idea is to take all of our Wolfram language technology, and indeed separately also the Alpha technology, and have it as a private instantiation that any organization can have as a computation hub. And it's kind of very powerful because you can imagine wiring all these pieces up and having it work with this sort of private computation hub. And one of the things that we do a lot with Alpha, people see the public Alpha, but actually a lot of what we're doing behind the scenes is we're working with organizations and using their data with them to make a private version of that so they can linguistically query their own data and get much more out of their own data. And it's interesting which industries have particularly come up with that. I mean, pharmaceuticals are very interested in that, retail is very interested in that in particular, and I think we're seeing more finance and things too. So here's the cool thing, if you have a private cloud, this might be a bit small, but you see, so for example, on this side we're saying we're going to compile data and we might want to feed that into a unified data network, create a historical model, we're trying to make predictions out of that data, set up interactive trade alerts. You know, this might be an example for an interactive trade alert for a financial institution. And the point is, if you've got a cloud, you can do all of these things inside that private cloud. And that's great because you can wire all these things together and start getting alerts and things coming out of it. And here's a really weird thing. So, and I think this is changing, but most organizations do not think of computation as a sort of enterprise thing. I mean, even computation, even the organizations where a lot of, like banks, for example, where it's kind of like important that computation is done right, and they typically have this very much. Everyone, has their own Excel spreadsheet, or it's sort of, somebody does it one way and somebody does another way. Yet we'd never allow that for CRM or ERP systems these days. Years ago, those were very much individual things. People had contact management, and that turned into a CRM system where the whole organization's contact setup was in some sort of enterprise structure. I think we are seeing the beginning of that with computation. So you need to think about what is the organization's computation, enterprise computation strategy. It's not good enough just to have all these little bits of computation around, because tying them together, this big unification, makes a huge difference. And these are some of the reasons why. I mean, it's kind of a long list. You kind of prevent knowledge silos, control data security, one code base but multiple interfaces, accurate computation. I won't do it here, but there's a thing I love to show, which I shouldn't be picking on Excel particularly, but it's really any numerical system. You take 0.2 and you do something like, as a starting value, you do something like 11 times x minus 2, right, where you start with 0.2. About 50, I should show this, but about 15 iterations down, the answer should always be 0.2 effectively, but about 15 iterations down, something like Excel will just blow up and it will say it's 10 to the 10, right? Wolfram language, for example, will track it and it will say at some point, I have no more significance to give you. I've run out of significant digits, but I'm tracking that, I know that. Right? So that's an example where if you've got screwy calculations, I mean, it's easy to see in that case because it's sort of straight in front of you, but if that was deep in a 10,000 line program, you'd be screwed potentially. So it's really quite important to know that you've got good, solid computation, and that's something we're certainly working hard to do. So one of our major projects at the moment is to piece together everything into this ultimate computation system. One of the good and bad things, so one of the questions always is with this, sort of, should you make it discrete or continuous? Should you have lots of systems that do little subsystems that do little individual bits? I think it's sort of time to integrate the whole thing, but you don't get every integration perfect. So you find that sort of individual systems might do something better. I think we're just starting to submerge some of the machine learning specialized systems in terms of what we can do with machine learning inside our ecosystem. But the point is, when you get to that point, you've got a really high plateau to fall back to if you're doing something slightly different. So one of the things that's hard for us is, this is kind of interesting, you normally think of sort of, I'm going to call these dualities, things that are either apps or platforms, or you think of symbolics or numerics. These are all distinct fields of, in a sense, computation or ways that software gets produced. Is it cloud or is it local? Is it data or is it expressions? One of the things we've tried to do is to join all of these up And so often people say to us, you know, is your system a development environment? Well, yes. Is it an end user deployment environment? Well, yes. Is it something you immediately use an end user? Well, yes. They're all the same thing, potentially. You want to be able to act on these things in all different levels. So we have these sort of, instead of having these discrete areas of what we do, we have these sort of dualities, a bit like particle wave duality when you're trying to describe light. It's kind of like it has characteristics of one, characteristics of another. It's useful to use one way of thinking about it sometimes and one way another time, but the real description of it is some abstract way of thinking about it which doesn't quite fit with any of these things, and that gives the sort of unification and the power that we're talking about. Just to round out, I mentioned earlier about how humans need to get a whole lot better at what they're doing. Just very briefly on this, as was mentioned, computer-based math got founded to try and, it's got a very simple mission. Rebuild the math curriculum assuming computers exist. Right? Seems pretty obvious. The problem is no country has yet done this anywhere in the world, or is even close to doing this. Right? You'd think it was obvious, but when you start to think about what do you actually need to know as a human to do maths, and the answer is not most of what you're being taught at school. But you need to know a whole bunch of other things you probably didn't know. So to give you a simple example of that, I don't think it's that useful to know the quadratic formula for solving a quadratic equation. I think there are 100 things more useful than that. For example, I think it's pretty useful to know what tools you might use for analyzing data. What kind of way you might use machine learning. But not just machine learning. What are all the other ways you might do analysis of a whole set of data? Nobody is being taught that at school today. They're being told to plot 5 data points by hand on a chart, not given 1 million data points and told to figure out what they can figure out about the data. So we've tried to, it's a very micro summary of the problem. I can go into that in more detail if people are interested. But we've been trying hard to rebuild this curriculum in such a way that we start with a problem. We use abstraction to mathematics where it's needed, and we give people the widest range of experience of actually using high-level maths that they can have. And we do that by chopping out a lot of the hand-calculating stuff that they're never going to use. It's a complicated area, but it is an area that the first countries and regions to adopt will, I think, kind of leapfrog others quite dramatically in terms of the ability to use modern automation. So, just a quick summary of where we come from in terms of, we launched Mathematica in 1988 with Steve Jobs, actually, 23rd of June. In fact, Steve Jobs who came up with the name Mathematica, funnily enough, in a conversation with my brother. We were bundled on his Next machines, which were the computers he built when he got fired from Apple the first time. And we very much stayed in touch all the way through, and in fact, of course, Siri came out, I think, the day before, or a few days before Steve died, actually, and of course we got integrated into Apple Siri with the Alpha project. Some of the things I've been talking about, computable documents, have come out in the last few years, and doing a lot more consulting as well as the technology as well. And we separated out the Wolfram language as a definitive separation from the rest of our ecosystem, in the sense that we want people to see that we have a language that you actually write stuff in. As I've said, everything's unified. But it's important people think that we actually have a language in which you can specify new things, and it's a very highly developed language. Actually, I have to embarrassingly say that the first project to try and separate the language was done, which we didn't act on properly, and there were some good reasons for that and some bad reasons on that. But anyway, that we had an intern in our US office in Urbana-Champaign, where we are, and the intern's summer project was to figure out how to separate the language. The name of this intern was Sergey Brin. This was just somewhat before he started Google. So anyway, we still have his project, and he thought we should separate it, so I guess we've finally done that. A little bit late, I'm afraid. So I guess the summary of what we're doing is we're the place where computation meets knowledge. And in a sense, our strategy is to build the ultimate computation ecosystem. And that's kind of the question I always like ending with is, what's your enterprise computation strategy? How are you going to move forward this use of ubiquitous computation to further the innovation you're all doing. Thanks very much.
Thank you, Conrad. That was awesome. Very inspiring.
Good. I'll try and get the tweet to work as well at some point.
Right. So, did you actually come to decide how Siri would sound like?
No. We're not doing the. So what happens with Siri is we don't do the Siri interpretation to voice. So we're not helping to help how it sounds like, but we are taking the text that Apple has sent us and interpreting that when they send it to us for. So it's when you do sort of knowledge-based queries, Apple filter it to us and send it to us.
So what was the most complicated part of integrating your system into Siri?
That's a good question. I think, well, okay, so I have to say actually Apple did a good job. They did quite a lot of the filtering and they did a pretty good job at setting it up to do that. I think in practice actually the integration wasn't too hard. It was a lot of technical details, how to make it work fast enough and do the right thing in the right place. I think that trying to set up the right domain so that it really worked nicely and smoothly between the things they wanted it to do, some of which was with Apple and not with us realistically. So I suppose the integration really wasn't so hard. In terms of the project in total, I think I've often said this, I think the understanding lags the amount of data. So I think there's more data than you can easily uncover with the understanding, if you see what I mean. So it's kind of like, the effort is, can you type in something and get the right understanding is a harder problem than actually, so to speak, piecing it together once you've got the understanding.
Right, and as far as I know, it's based on Wolfram language, right?
Correct.
So could you just briefly describe for us what makes it so special?
Wolfram language.
Yes.
I suppose one way to put it is, there's several points to it. One is algorithms are included. So we kind of have a huge range of the algorithms that are there. You could just immediately call it up. And I could do a quick demo actually. I did, maybe I should do a quick demo in a moment of that. But I think the other thing is we've always had the belief of a multi-paradigm language. So you can program Wolfram language, procedurally or functionally or with pattern matching. It's all pieced together in a sort of unified syntax. And it's, I think those two together have great power. Again, early on, people were forcing us, you should make it much easier for the computer. So make the language lower level so it's easier for the computer. And we kind of resisted that because computers are now big, beefy animals. So I think it's being able to just talk directly at different levels of abstraction and know that things are built in. And let me just quickly see if I can rustle up this may or may not work. It's maybe another demo that doesn't work, which was very annoying.
We'll try it.
Actually, what I might do is let me get rid of that image actually. Let me let's see if this was, so I'm going to do what I was going to do is I thought you'd probably be fairly bored of my face by now, so I was going to try and block it out. Let's just see if I can get this working. Okay, so there I am. Let me put the text a little bit bigger maybe. Can you see the current image thing up here? It's a little bit small. Let me make it a little bit bigger still. So what I was just going to see if I can write what is going on here. Should be making that bigger. Okay. Anyway, what I was going to do is set this up. So can you see that, or is that too small for me? Okay, fine. So let me say, what I'm going to do is say something like, I would like me to be the current image, and then I would like to do something like show, let's say, me, as well as a graphic, let's say of graphics of, let's say, a rectangle. So what I want to do is put a rectangle over my face, So I want to find the face in the image, and looks like it's find faces of on me, and hopefully show that and put it together. And I've made some mistake, which is because I'm trying to do this live, and that usually happens. There we go. So I managed fairly successfully there to combine an algorithm of finding faces, applying a rectangle to that, putting graphics around it, showing it, turning it into the current image, and so forth. And that's the sort of thing you can do with our language, because you can piece these things together.
And if you now had a second face, it would not with the rectangle?
It would actually, I think. You can try. You want to try? Go try. You come up and see. I think it will, because I said it's the find faces thing. So hopefully, see if we can both get rectangles. I think it will do too. It's now seemed to prefer your face to my face.
I don't know why.
Right, but it should probably do two with this particular algorithm. So anyway.
But me is singular. It is there's only one me.
No, because the me is actually the whole current image.
Okay.
So it should be detecting both. And actually, I know sometimes it detects other things, of course, as faces as well. But anyway, that's an example of the Wolfram language in action, so to speak.
Awesome. Conrad, everyone, another question. Your brother Stephen and his son participated in creating the alien language in the film Arrival. Right?
Which I still have to see. I have yet to see the movie. I need to get my act together.
Right. So what I'd like to ask you is, how can maths and coding create new levels of understanding worldwide?
It's an interesting question. I think the deep answer to that is it's because it's a way of thinking about things in an abstract way, and abstraction is incredibly powerful for allowing us to put ideas from different fields together. One of the failings in education, maths education today, is we typically start with the abstract thing first. And there are a small number of students who really like that, and really like abstraction for its own sake. And that's great. I'm all for them liking that. I'm not negative about that. I guess I was possibly one of those too. But, to some extent anyway. But actually the vast majority of people would like to see an actual real problem they can relate to at that point in life. And the point then is, you can just, if you've got a problem, so like in Estonia, for the project we started doing with this computer-based maths, we have a whole list of problems. The first problem is, am I normal? A problem for teenagers to think about. Now, you might think that's not a problem that maths can help you with. Maybe it is, maybe it isn't. But the point is to give the idea that you're starting with a real problem, and then just talking about it in English or German or Estonian or whatever won't necessarily get you the maximum distance. So what you need to do then is abstract it to a language that allows you to be very specific and pull together different ideas, but in the same structure. And in a sense, that's what maths has done as a part of its problem solving. But maths is a rather narrow language. I mean, you can think of maths as a language. Traditional maths notation in particular is a language, but it's a very narrow language. It doesn't allow you to write down processes very well. It allows you to write down expressions and steps to those expressions, but it doesn't allow you to write algorithms in general down particularly well. Modern coding languages, obviously we're trying hard to make Wolfram language this, allow you to write these things down very directly, this much wider gamut. And so I think that's how it helps people to kind of get much further by learning how to do these things. So coding is partly about learning how to abstract. And it's partly about actually knowing the language, the detail of how to get your computer to do that.
Right. Another question. You have the Wolfram problem generator, right, as part of Wolfram Alfa, which basically helps you generate random tasks for statistics or algebra, for example. How complex was the creation of the software, and how is it being used now?
It's not that complex for us to create, realistically, because it's like my image identify thing. It's kind of like we've got all the pieces there. It's I don't know exactly how long. It's a few weeks of work at that. I think we're really starting to see the beginning of the use of that. I mean, part of it is just one of the problems we have in reforming and stuff with education is we have two totally different strategies in our company, which I think are completely it's coherent to have both. One is, let's take our technology and do the best we can using our technology with today's curriculum. Because we're trying to help people do as well as they can with whatever they're having to do. And part of that is, for example, having problem generators generates different problems, they can try different problems, they can understand how to do those. The second completely different strategy is fix the curriculum. Fix what people are actually doing, which is what I've been doing with computer-based maths. Those are perfectly, I'm fine with both of those. And I guess the problem generator at this stage is probably in the former of those. It's trying to help people do today's maths. The tricky thing, I think, which we haven't got quite the technology for yet, is, for the computer-based maths, what you want is very open-ended questions, very open-ended adaptive learning. And it's not quite there. Wolfram Alfa is closer than I think pretty much anything else. You can type a sort of slightly fuzzy thing in and it'll figure out what you meant, turn it into a symbolic thing, compare it with what it was supposed to be, potentially take you to the next adaptive stage that you might need to learn. But it's a fairly minimal set of things at this point, and we'd like to make that a very general way of allowing adaptivity to happen, and we're some ways away from that.
Yeah, right, which is great for the school education, but what do you do with people who are in their 30s, come from humanities, and still want to adopt a new way of thinking?
Well, I think we're the computer-based maths project is trying to address, it's been focused on schools, although I think we're a lot focusing on adult education now as well, for all sorts of reasons. I just think it's the same problem, which is that, I've had so many people tell me after they've heard my TED Talk or other things on the computer-based maths that it's just like, my gosh, I never realized that's what the subject was. This is the first guy who explained to me why maths has any relevance to my life. So I think there's just a lot of basic, here's what it can do for you, here's where it applies, here's what you might do with it. Here are the 4 steps I talk about of doing maths. And I kind of think that this is something that can be learned at any age. So we'll be starting with computer-based maths to put out more sort of consumer level parts to that when we can figure out how to do that in an effective way, and MOOCs and things like that. And I think we'll hope to help, and we're also working a lot with larger organizations starting to work with them to deploy the kind of thinking we're talking about into them, so that their people can be trained on this. I think the training of coding has become a big thing. Go and take a coding thing for 10 weeks and you'll get a better job, type of, particularly in the US. That's fine as far as it goes, but the problem is that that it's just, that's a very particular skill. You've really got to understand more about what to be skeptical of, what to do under the surface, and that's something right the way up all the age groups. And actually, I slightly, I guess, aggressively wrote a blog post recently about post-truth, and how I believe that there's a connection between post-truth, and so-called people just not looking at any logic or facts or anything and somehow drawing conclusions. There's a connection with that and their failure of maths education, because they don't know how to examine the experts or look at people in general don't know what questions to ask to figure out whether they're being told bullshit or not. And it's quite hard for most people in this room, and many technical people here will know how to do that. I don't really believe what this data scientist is telling me, or this environmentalist, or this politician. But it's quite hard for most of the public to do that. So then they flip-flop between saying, we believe every expert because they are an expert, or we believe nobody, however sensible what they're saying might be.
So as we see, a lot of problems lie in their own tech education or maths education. If you could do absolutely anything, how would you design the educational system? I know that's a huge question.
That's a huge question. Well, a few things I would do. There are different layers of that. One is the subjects, I think, are not the right things. I think there are ways of thinking that you need to engender across subjects. So computational thinking, what I'm particularly interested in, but that's not the only type. And I think this sort of division between history and geography, and I think you need projects that take up at least quite a lot of the time. The other thing I think, which is a very tricky thing, and when we were talking on the ride over here about this, what is mainstream and what is something that people should try, and if they like it, they go on with it, and if they don't like it, they drop it. think there's a lot of confusion in schools about this. So there are things you need for societal benefit and for your own advancement. I would put the right kind of maths in some of that. I think some historical understanding is important for society. You need to know your own language and how to communicate. Then there are things that, you know, you may enjoy or you may not enjoy, but it's not going to kill you if you don't. It's the same, you know, how hard do I push my daughter to learn the piano and the violin? Well, if I don't push her at all, she may never discover that those things might be fun. And she has to do a certain amount of practice, which may be very boring, in order to get to the point where she might enjoy playing a nice piece on the piano, right? But it's quite hard to know where that is. But on the other hand, if she really just doesn't like it in the end, it's not, you know, she can survive perfectly well in life without being able to play the piano. It's hard for her to survive in life without being able to string a sentence together and communicate with other human beings. So I think there are different aspects. So I would urge very much more thinking about what's important at, you know, as a mainstream thing you've got to do, and then cycle through these great things to show people and get them excited about and allow a much greater variety in schools of what can be done, and of course outside schools. Then there's the whole problem of, you know, should they be in school, should they be not in school? How do you restructure that? I think probably the final thing I would say in a sort of very quick summary is, I think teachers are important, but they're doing mostly, they're trying to do the wrong kind of thing at the moment. They're trying to, at the moment, be the fountain of all knowledge. And what they should be being is CEOs of the classroom. Like they're trying to, they don't know everything.
That's a good tweet if you're going to tweet.
So the teachers don't know anything. That's fine. They don't know everything. They need to have the confidence to do that and to help their students, to be the person who can help their students forward, like a CEO helps to figure out how do we solve this problem. And I think, and many good teachers, you know, do operate in that mode, but I think that that often is not what's happening, and I think that's not helpful.
Right, thank you, Conrad.
Thank you.
For your questions. Who was the first one? Please.
Thank you for your talk. To go back to one of your points from the slides, when I first got into, I did some mathematical modeling in my career. One of my biggest shocks when I first got into it was how hard it was to sell decision makers on the results. And the often most successful approach I found was what you discussed in one of your slides with the GUI that allows them to kind of play and build up their own intuition, but that was contingent upon my ability to explain unintuitive impacts. And with the move to machine learning, I often lose that capacity to explain. And given the last psychological research I saw, I think given that the human mind tends to overweight negative experiences, I need to be right 5 to 10 times for every time I'm wrong to maintain that buy-in. So with this progression, and machine learning sadly doesn't always get me that ratio. So it's an interesting situation where my accuracy might get better, my ability to sell it gets worse.
It's a very, very interesting point and analysis. I think, I mean, I always think I mean, I find this myself, like if I drive myself somewhere, I tend to know the route better. So it's kind of like the same. If you can allow the reader to drive, that's a big plus. Look, I think machine learning is, and one of the things is that, I mean, I think one needs to walk through the process of how the thing's working with the person to try and get them to understand what one can and can't understand about it. But as you say, it's tricky with people who are not sort of educated in thinking that way. I would also say that, you know, at the moment everything's machine learning. You know, everybody is. I'm all for hybrid solutions to things. I think that we're seeing this actually with our technology. We've got great machine learning, we've just been building this all in, and that's fantastic. But what's really exciting is a mixed sort of algorithmic machine learning, if I can put it that way, approach often. Just like in solving problems, we often have a mixed symbolic numeric approach. So I think, I mean, I guess I find what's exciting for us is ever better interfaces to the information and ever better ways to be able to immediately zoom out and show something the person's asking. I know one thing that fascinates people sometimes where we're introducing our technology to organizations, and I'm not as good as some of my colleagues now, but it's just amazing. They say, well, so for example, what happens if we, you know, I don't know, make this a 3D version of your interactive? And as they're talking, the person's changing it. we're programming it in real time. And that's very exciting. And that I think that helps people to feel more comfortable, because they feel like stuff can be reacted to and it isn't just totally a black box. So that's a very partial answer to your important and interesting analysis.
Thank you.
Thanks for your talk, very inspiring, yes. I have a more broad, I would like to talk about a more broader look in the future. So the artificial intelligence discussions are all over the media. So Bill Gates, Stephen Hawking, Elon Musk are now saying, okay, all this AI, this might kill us in the future. So what's your idea about that?
I'm less pessimistic. I mean, you know, it might, but I think that the more usual, I mean, and maybe this time it'll be different. In the past, when there's been a huge revolution of technology, people have thought that'll be the end of some total tranche of human. And in some sense it is, but the point is that humans have always managed to go to another level up and do something different from what the machinery is doing. Now, maybe this time that'll fail. I kind of think it won't, as long as humans do the right way of trying to sort of deal with that. Now, that isn't to say there won't be quite a lot of pain along the way. You know, I mean, when agriculture industrialized, there were a lot of people who didn't have jobs for a long time. And it wasn't like there wasn't pain along the way, self-driving cars, and then we don't have taxi drivers and things, truck drivers. But I think in terms of the longer term, overall, I have a feeling that at least, you know, humans will find a good way to organize and interact with the AI that they build. But we'll have to see. So I don't know, I think people often run off with, I don't know, gloomy versions of the future, and, you know, anything's possible. But I tend to think humans have more capacity for change than people give them credit for.
Thank you. Other questions? You want to ask a question?
Thank you. First of all, yeah, thank you for your talk. Very inspiring, and definitely I will go back and see what Wolfram Alfa can do for me. I'll check it out. So good sales job as well.
Okay.
I want to focus on your computer-based math initiative a little bit. Two very quick questions. One, you mentioned those categories, what you absolutely need to learn and what is kind of nice to have. Where would you put introduction to coding? I would put it in the first category, mandatory, would you agree?
Yes.
And very quickly, second question on that, follow-up, is you talked about the different countries are on a different scale in how well they are, and can you comment a bit which countries are doing really well, which countries aren't doing well? Maybe focus on Germany, the United States,
sure.
and UK as examples.
Well, those ones I'm afraid are not in my high category. None of them. Sorry, your first, well, let me take the second.
Introduction to coding.
Yes. Coding, I think, is important. In fact, more important than governments have given it credit for. Because I think it's sort of like the handwriting of the modern age for technical things. It's like, how do you write down the abstraction? I might just flick out, actually, we'll flick up while I'm talking. My face isn't blocked out here. I can probably flick up actually the talk I had earlier, because there was a slide I wanted to show which might help to make that clearer. Let me see if I can close this. And the point is, I think of sort of maths in a, as sort of, three different steps, four different steps rather, in solving a problem. And coding is particularly important in what I call step 2. Let me just fire up this, because I think this might help us here. I think I showed this somewhere. Okay, so this is the slide I was looking for. So, sorry, let me make it go full screen. Oh, we've got it, right. So the point is, what you're doing, I think, in maths, is you are sort of defining questions. If I go on talking in this room and it's sealed, how long can we survive here for? Then we're translating that to abstraction. Then we're computing answers from that, in a sense, by turning the abstract question to an abstract answer. And then we're interpreting the results. Did this, the answer was -3, well maybe I did something wrong, this doesn't seem to make a lot of sense. Maybe it was 3, it meant 3 hours, whatever. And the problem is this section. This is probably the hardest step. And you need something to abstract this to. Traditional mathematical notation doesn't do the trick because, as I said, it's too narrow. So I think that's where you need to abstract to code. And in a sense, you know, and you may have different languages of code to abstract to, but code, in a sense, allows you to both tell the computer what to do, but it also allows you to explain abstractly what it is you want done. And so in a sense, that is the thing. Now, when you talk about coding, though, it's a bit confusing because some people mean by coding just, you know, given that you've done this step 2, how do you then somehow write this down so the computer understands it? And some people think about coding as including the abstraction. And so there's a bit of confusion there, and I think that still needs to be ironed out. And the big problem, while I've got this up, the big problem in our current education system is we spend all of our time doing step 3 by hand, as opposed to drown out these other steps, in particular the abstraction. So back to the countries. No country in the world has really understood that you need to rebuild the maths, assuming computers do the calculating. Right. You know, countries like Singapore and I mean, I'll pick Singapore, but there are other countries as well you can pick. I think I've done a good job of moving the bar on existing maths, sort of, and how you deliver it pedagogically fairly well. I don't know too much about Germany. I know that the UK, you know, it's very UK-like. In the UK, what happens is everybody on the ground says that, you know, everybody who runs this are idiots. And they talk to each other for a long time about how it's all idiotic, but they don't actually get the thing changed until suddenly it all blows up and changes quite quickly. But that may be 10 years down the road. The way in which it will change maybe in Germany will be different. But I do think all these, I mean, I'm afraid the countries that are sort of in the middle of, I mean, to pick a PISA table, not the PISA OECD thing, not to pick that as a standard, but countries that are kind of in the middle of PISA, which would include Germany, the UK, and the US, sort of say it's too risky to change. But somehow, you know, it's kind of like we're not high enough up to do anything. So we found most interest in the change from the very top of the table and the bottom. Estonia, for example, is very high, even with their existing maths, but they realize it needs to change. So I think the change is going to have to come outside of government in most countries. And the thing I'm really employing governments to do is change the ecosystem of innovation in education so that innovation can actually happen. At the moment, the assessments lock everything down because everything gets taught to assessments. And the problem with that is you can't change the subject. Because however nice some school wants to do computer-based maths, in the end they've got to take the same old assessment. So that's a quick summary anyway of the...
Thank you.
Thank you.
It's perfect timing because that slide is brilliant for my question. Something like 1.2 and 4.1. Because my question was how you teach people to ask the right questions. And because defining things and working on things without having the proper topic or the real problem behind is what I always find very difficult to convince people, like do more than one loop, like what people say is not what they mean and all these little things.
Right,
and
so I mean, to give you an example of that one, so we've been building materials to try and do this. And it's very hard, it's taken us a long time because you're trying to work out what is it people need to know, how do they need to know, and so forth. So to give you a specific example on that one, there was a module we built called How Can I Convince You? This is for the, so this is the teacher version. We've also made it in nice electronic computable documents and everything else because we like doing stuff like that. And so this is trying to lead people through how might you get the experience of what happens here. So this is the teacher version. So all the orange things are to do with what teachers might do, etc., etc. Anyway, what the student might do in this. Well, maybe I should just make the student version live here. Let's see if that'll work. Oh, there we go. There's the student version produced. Okay, so. This was an example, which was to say, here are 4 quarters of sales data, and here's the pie chart. Now, you are the sales manager, and I'll explain the point in this moment. The point is you want to try and, it turns out quarter 4 was a bit worse than quarter 3. 813 instead of 821. Can you make your sales chart look like it was better? Okay, so you know there are lots of tricks to this. You can sort of make it, let's make it 3D and let's make it go, you know, I don't know what we're doing here, but let's zoom it one way or another, and I guess what I want to do is zoom in or something. But anyway, okay, so maybe if we rotate it, then actually that does look a bit bigger than the others. So why are we asking students to do this? Because it's going to be done on them every day of the week. Better that they know how to do it from the inside and see what the trick is. So what we found, I mean, this is a very simple example of many different things, but you know, it seems to me the way you get experience of how to handle stuff in life is by actually experiencing as much as you can, and accelerating that experience and giving people a lot of the edge cases that they might meet in as an imaginative way as possible. And you know, if you want to know how to handle a car when it's snowing, when it skids around the corner, you can look at the physics of it and you can hear the theory of it. The best thing to do is actually just learn how to handle it and know what to do. And you know, it's kind of like, that's, I guess, how I think. And if you look at things like, you know, to give a good example, flight simulation. I mean, it's amazing, you know, how safety things have been improved by flight simulation, because you're experiencing all those things ahead of when they really happen in anger.
Conrad, thanks a lot. And thanks a lot, not only for the presentation, but for making my life 25 years ago with my little Next computer.
Okay, oh, very good. You were a Next computer.
Because I loved your 3D graphics, and they ended up in my thesis, so that was...
Oh, fantastic. Okay, very nice.
So it's a whole different experience. But what I wanted to ask you is, what do you think about open source? Because your system is still a closed system. It's fantastic. It was at least at that time. I'm sure it's much better today. And at the same time, today when you look at machine learning, you see a lot of companies moving into publishing their source code. There is a lot of collaboration, and that's what these companies realized is necessary to get to the next frontier. And I haven't seen that yet with Wolfram. So
well, actually, no, it's a great question.
What's the path forward?
Yeah, so it's a great question. Actually, we are open sourcing much of, you know, things we can, like our language. So you'll see our language is out there. It's a, you know, you can do stuff. There's free ways to use it immediately with our cloud technology and so forth. So we're moving much closer to that where we can. The big thing I think about open source is one's got to realize it's a business model. And like all business models, it's got a domain where it works really well. It was a fairly new business model in the form it was, you know, in recent years. And I think it's worked great for certain areas. And I think there are areas where it doesn't work so well. I mean, one of the problems with what we're doing is, if you want an incredibly coherent setup across a huge number of different areas, it's hard to do that with open source. I mean, I wish we could do that, right? Because I would love to see our system grow much more effectively, in a sense, by open sourcing many pieces of it, but it's really hard to do that. And so what you end up with is, you know, for certain things where kind of the coherence is less important than sort of the rapid growth in lots of directions, I think open source can work extremely well. I think that's not been our kind of view of at least where we've got to. Now I think, to say that though, there is a point at which you kind of get to a level of structure where if people kind of can see that structure and they can act on it and they can build out from it without messing up the structure. And I mean, you know, this isn't exactly open source, but I mean, I do think, for example, if you look at the you know, the Apple Store, the fact that they laid out what really happened with apps was a great start to how the apps actually happened, and would have made it much harder for follow-ons for that to have anything real happen there. So it's partly timing and it's partly what it is. And I think it's also partly that, from our point of view, we are actually trying to do quite a lot more of those sorts of open source areas, in particular our language.
Yeah, my question goes back a little bit to the topic of changing math education and your project. So I have the slight impression everybody in this room is on the same page that it needs to happen. So let's just assume, let's say the Ministry of Education in Germany would be on the same page, and they ask you as a consultant what the prerequisite is to make it happen. Like maybe the 3 things that need to change immediately, that needs to happen in order to take a step forward, and maybe also what you think, how long does it need to...
Okay, these are great questions. I think, look, the number one thing I would say is take a part of the curriculum and let's make a completely new version of it and make sure the assessment that's supposed to be attached to that is also changed at the same time. And you know, you don't have to do everything at once, but let's start with some big chunk that you can take and do that. Now obviously you've got to make sure that people have computing available. It doesn't matter whether it's their own, you know, personal computing or whether it's in the schools. I think there's a lot of fear then, will the teachers make it? Our experiences so far is actually, you know, not every teacher makes it, but a good fraction actually, it's less scary than they might think. And the thing that makes it a lot less scary is most math teachers, when they stand in front of the class, have no idea why they're teaching what they're teaching if you dig down. They don't really know what it's for. When they start to understand, well, here's a problem that I understand what the problem actually is that I'm trying to get across, and I'm going to help, and we have good backup materials and things for that, actually it becomes more fun and less scary in many cases. So, I mean, those would be the immediate steps. I mean, another thing that we've done sort of hard worked on is in order to figure that out, and so we've gone a long way in trying to figure out kind of like what it is you need to figure out in order to make the assessments. What are you trying to assess? And so, for example, here we've made a kind of complete list of kind of the outcomes that are required in mainstream maths. And I think that's an important prerequisite to agree upon. What is it you're trying to get as the outcomes? And you can see this on our site. It's a little hidden at the moment, but you know, and then things like confidence to tackle new problems and things. So those would be the steps I would immediately try to take, and I would probably pick slightly older kids to start with. I would say that the early primary is probably less messed up than the later, you know, like middle and secondary. And that's the way I would try. The other thing I would say is, and I know Finland are trying this, you know, manage to, you know, use the maths and the computational thinking and the coding across all the other subjects as much as possible. So let's have problem sets that apply to history and geography and linguistics and everything, and try and insert those in those lessons. So kind of break those subject barriers down.
Thank you for your talk. My question also aims in the direction of open source. Are there plans to open source either the computational knowledge base or the source code of Wolfram Alfa as part of your heritage?
The source code for Wolfram Alfa. Gosh, that's a complicated. I mean, one of the problems is we've often published parts of our, not the whole source code, but parts of our, you know, sort of source of our language. And the trouble is, it's sort of hard for, I mean, just dumping it all out. It's a bit like my saying earlier, dumping all the data out there in one go doesn't get, I mean, I think what you want is accessibility to this, to know how to change it and what you can do in the future. It's an interesting question. We haven't really gone into the heritage of Wolfram Alfa yet. I guess we still think it's a very up and going thing. But you know, I think the interesting question there is, how does one make sure that it's openly accessible, as it is at the moment, to the broadest range of people, both to use and to build on? And I'm not sure that sort of dumping out the source code is the realistic way of achieving that, but it's something that we should think about for, as you say, for our heritage. So.
And the other part, the knowledge base?
Oh, the knowledge base itself. I mean, in many ways that is accessible. I mean, obviously directly. Some of it's accessible. I mean, it's, I mean, you can access individual bits of it. We haven't sort of said you can download the whole knowledge base at one go. But I think what we're trying to do is unlock individual works for that. What we want to do, realistically, is get enough, and we get enough sort of income coming in from the very large-scale industrial uses of that it can fund building more of the computable knowledge out. I mean, one of the problems with the knowledge setup as we have at the moment, and this is improving, but one of the things that's expensive is getting the knowledge computable. So in order to make the knowledge in such a way that Alpha works with it is actually the most expensive part of the Alpha project. And one of the problems is how to improve that, make that work faster, you know, to get new knowledge in, how to expand that at the maximum rate. And you know, I don't think we've got the perfect business model for that in a sense, but I think that that's sort of what we want to do and make that as accessible as possible.
Thank you so much, guys. Please give a warm round of applause.
Thank you very much.
Just one more short thing. You can follow us on Burda Bootcamp on Twitter and Facebook. You will see all the video which you've done there as well. And if you're thinking about hosting your own meetup, like talk to me or to Patrick, the guy in the red shirt. That's it. Thanks for being with us. Thank you.
Thank you. Okay, great. Very good. Thank you. Very nice.